why it's not possible to photograph our galaxy from the outside. When we talk about our galaxy, the Milky Way, you've surely seen visuals like these. As you can guess, none of these are real photographs. They're all artists' impressions. Yep, pretty pictures, but not actual snapshots. In fact, forget photographing the Milky Way from the outside. When we look at the portion we can truly observe with the naked eye, all the stars we see fall inside this red circle. With the naked eye, we can typically see stars only a few thousand light years away. And a few thousand light years is a tiny fraction of our galaxy's approximately 100,000 light year diameter. Even the Kepler Space Telescope, launched in 2009 and operating until 2018, discovered 2,778 exoplanets within a field just approximately 3,000 light years across during its mission. So if that's our observational reality, how do we know the Milky Way's shape looks like the one in that familiar illustration? Trying to infer the Milky Way's shape without stepping outside it is like trying to find your way inside a vast forest. You're lost in the woods and the trees are all you can see. That sounds tough, but it's not impossible. For example, in the 200s BCE, the ancient Greek scholar Eratosthenes deduced that Earth is round and even estimated Earth's circumference with surprisingly small error. We can learn our galaxy's shape and size in a similar spirit, but don't worry. In this video, instead of wrestling with complicated math and physics, we'll take an enjoyable journey into the depths of the universe. No heavy equations today. Scout's honor, the Milky Way and its arch. If you head somewhere truly dark, no nearby light sources at all, and look up, you'll notice a softly glowing, misty structure stretching across the sky like a giant arch. You can't miss it. It's like a luminous bridge from horizon to horizon. For thousands of years, people have come up with different ideas about what this strange feature might be. The Greeks thought this band was milk spurting from the goddess Hera's breast, hence the English term Milky Way. Different cultures told different stories. The Egyptians imagined cow's milk. Australian Aboriginal peoples saw a river in the sky. Today we know that what we're seeing is a small portion of one of our galaxy's spiral arms, composed of hundreds of billions of stars. And in fact, even without complex calculations, we can make some early inferences about our galaxy's shape just by studying this arch in the sky. Galaxy types: elliptical, spiral, irregular. Even if we can't see our own galaxy from the outside, we can observe other galaxies. Broadly speaking, we encounter three main types: elliptical, spiral, and irregular. Our galaxy could have been any of these. Our most important clue is that long arching band in the sky. If the Milky Way were elliptical, we'd expect stars to be evenly distributed across the entire sky. In other words, no matter where we were inside an elliptical galaxy, we wouldn't see a band-like structure. The same goes broadly for irregular galaxies. But when we look up, we clearly see stars concentrated along a single swath, which points not to a spherical distribution, but to a flat disk. And we can verify this with examples. Many disk-shaped galaxies are visible in the night sky. Moreover, since spiral galaxies can be oriented at random angles relative to us, we can observe them from very different perspectives. Spiral galaxies from different angles. In M51, the galaxy's disk is oriented face-on. We're looking straight down onto it. In M81, the disk is also rotated toward us, but at a slight tilt. For Andromeda, the angle is narrower, though we can still make out its spiral arms. With the Sombrero galaxy, we're looking almost edge-on. Because of that, the spiral arms are hard to distinguish, but the flat disk shape is still obvious. So what if we view a spiral exactly edge-on? NGC 891 is a perfect example. At 30 million light years away, it shows us the profile of a disk. We can't see the arms, but we can see the central bulge evidence that stars are more densely packed in the center and thin out toward the edges. That's a strong clue that this is a spiral galaxy, even when the arms themselves aren't visible. Returning to the Milky Way, we only see a small fraction of its band in our night sky. To reach a firm conclusion, we need to observe every direction in the sky from our vantage point. We can't do that with our eyes, of course, but space telescopes can. Indeed, between 2014 and 2016, the Gaia satellite scanned the entire sky in 3 dimensions. When we project that 3D data into a panoramic image, we get a complete all-sky view, the most detailed photograph of the Milky Way from where we sit. The result is jaw-dropping, a cosmic group photo with us stuck in the front row. I suspect you now see where this is going and why I showed those earlier galaxy images. The similarity between NGC 891 and this Milky Way panorama is no coincidence. In both, we see a flat structure with a prominent bulge near the middle. Since we also know other galaxy types exist, this image allows us to conclude that the Milky Way is a disc-shaped spiral galaxy. Looking at our galaxy's central bulge in that panorama, we can also infer that this region marks the center of the Milky Way. And when we peer into that center with telescopes, we find gas moving at approximately 30% the speed of light and stars orbiting around something. The only thing that could influence its surroundings that strongly is a supermassive black hole with a mass of about 4 million suns. Yes, this is the region of Sagittarius A, and in recent years, we even managed to photograph it. That's right, we literally took a picture of our galaxy's heart. Considering Gaia's image of the bulge and the supermassive black hole detected there, the conclusion that this bulge marks the center and that the Milky Way is spiral grows even stronger. Herschel's first Milky Way map. If we now have a good idea of our galaxy's shape and type, the next question pops up immediately. Where exactly are we inside this spiral? The first systematic step toward mapping our galaxy was taken in 1785 by the astronomer William Herschel. He divided the sky into 683 regions and counted the stars in each, reasoning that star counts should be denser toward the center and sparser toward the edges. Based on this density distribution, he tried to infer where we were located. However, across the regions Herschel surveyed, the star densities appeared almost uniform. From that, he concluded that the sun sits at the center of the Milky Way. Today, we know that map was very wrong. Why was Herschel's map so far off? Because he was unaware of the interstellar dust that thickens toward the center of the Milky Way. Here's the gotcha. Dust was blocking his view, so the center looked emptier than it really was. These dust lanes hide huge numbers of stars from Earth's line of sight. So when Herschel looked toward the center, he couldn't see the very stars he needed to include in his density map, and his conclusion ended up incorrect. Even so, Herschel's work provided important clues about our galaxy's shape. Despite misplacing the sun, he correctly hinted that the Milky Way is disk-like. One more historical detail matters. Till the early 20th century, many believed the Milky Way constituted the entire universe. Herschel himself thought his map was a map of everything, with the sun at the center. Other galaxies seen at the time were called nebulae because they looked like fuzzy clouds in the sky, and most people assumed they lay inside the Milky Way. A few astronomers, like Heber Curtis, argued that some nebulae were actually separate galaxies far beyond the Milky Way, but nobody had a definitive way to measure their distances yet. How Cepheid variables let us measure distances. Certain stars pulsate, they expand and contract periodically, causing their brightness to vary as seen from Earth. Early in the 20th century, Henrietta Leavitt discovered a relationship between a Cepheid's pulsation period and its absolute luminosity. Determining a star's absolute brightness is critical because when we look at a star, the immediate data we get is its apparent brightness, how bright it looks from Earth. Think of a candle whose true light output you know at 1 meter. If you move farther away, it appears dimmer. If you know the candle's true output, then by measuring how bright it appears, you can calculate how far away it is. That's why Leavitt's discovery was revolutionary. By connecting period to absolute luminosity, it let us determine a Cepheid's true brightness and thus compute its distance from how bright it appears. Harlow Shapley and globular clusters. Astronomer Harlow Shapley had the insight to apply this technique to globular clusters, dense, compact groupings of stars. For example, the Messier 80 globular cluster spans only about 96 light-years across, yet contains hundreds of thousands of stars. Shapley noticed that globular clusters in our galaxy are distributed across a roughly spherical region, but are much more numerous in the direction of Sagittarius. That observation was crucial for locating our position. If Earth were actually at the Milky Way's center, as Herschel's map implied, globular clusters would be evenly scattered across the sky. Instead, their concentration in one part of the sky implied that the galactic center must lie far from us, near Sagittarius. For the first time, we understood that we were not at the center of the Milky Way, let alone the universe. In other words, we're not center stage. Based on his calculations, Shapley estimated that the Sun and Earth sit about 50,000 light-years from the Milky Way's center. That's somewhat overstated. Today's more precise measurements put us about 26,000 light-years from the center. But this was the first realistic step toward the Milky Way's true scale and our place within it. And Shapley was absolutely right that the center lies towards Sagittarius, the region where we now know Sagittarius A star, the supermassive black hole, resides. How we map the Milky Way's spiral arms. Up to now, much of what we knew was limited by what I mentioned earlier, interstellar gas and dust. If we think back to the forest analogy, being inside the Milky Way is like being inside a very dense forest, and the mist among the trees hides many of the distant parts. But that's only true for visible light. Other wavelengths, radio and infrared, can pass through much of that gas and dust. With telescopes sensitive to different wavelengths, we can see through those dusty regions. That's exactly how we imaged Sagittarius A star with an array of radio telescopes. The birth of radio astronomy in the 1930s was a total game changer. In the 1950s, astronomers used radio telescopes to study gas and dust regions where stars are born, giving us one of the most effective ways to map the Milky Way, find the young stars. As the galaxy rotates, gas and dust in the spiral arms compress, triggering star formation. So if a region shows a high fraction of young stars, it's a good bet a spiral arm runs through it. Observations from Gaia, which is still operating, measuring distances and motions for over 1 billion stars, support this picture. Our address in the galaxy, the Orion Arm. Putting all this together, maps indicate that our solar system sits between the Perseus, Hero Arm, and the Sagittarius, Archer Arm, between them but not in empty space. We lie on the edge of a smaller spur called the Orion Arm, or Orion Spur. This feature is thought to be roughly 3,500 light-years wide and about 10,000 light-years long. So the next time you're under a truly dark sky and you look up, remember, that soft band you see is just a tiny patch of a spiral galaxy, more than 100,000 light-years across, a dust-shrouded sliver of a minor arm. Long ago, people could only tell stories about that site. Some even used it to reinforce the belief that we sit at the center of the universe. Today, it points us to the opposite conclusion. We are nowhere near the center, not even of our own galaxy. We're not the main character. We're a background extra on the Milky Way's grand stage.